Okay, well, we'll begin. This is the winter 2015 seminar, group dynamics seminar, and the topic for the semester is biosocial methods. And we've arranged a diverse set of speakers from many disciplines, which include genetics, statistics, biostatistics, political science, economics, social psychology, developmental psychology. And each week it'll be a different perspective on methods that are used that integrate biology and social and behavioral sciences. So I hope this is an entertaining and stimulating semester for us attending. Normally the first week, the group dynamics norm is for the organizer, which is me in this case, to give an overview of the seminar series and how all the speakers fit in. But because of the various schedules of the speakers, I'm going to defer that discussion until February 9th, when I'll also talk about the new Biosocial Methods Collaborative that's on campus. And so today is somewhat special because the seminar is jointly sponsored between RCGD and the Institute for Healthcare and Innovation, Healthcare Policy and Innovation here at the University of Michigan. And we have the director of IHPI here, John Ianian. And this is also, this talk today is being streamed over at the old Pfizer complex where IHPI is housed. So we have a set of colleagues over there listening in to today's talk. There's also a graduate seminar associated with this speaker series, and that will go on from 5 to 6:30 right after the talk. So for those students who are enrolled or interested in enrolling, just see me afterwards and we'll go over to a different room where we will go over the syllabus and the details of the graduate seminar. What I thought I would do today, though, is to give at least a little bit of introduction behind today's topic of heterogeneity and why it's being selected as one of the topics to be discussed this semester on biosocial methods. So let me switch over to a few PowerPoint slides. And I'll try not to take too much time from today's speaker. There we go. All right, a little bit of introduction as to why we need a biosocial methods collaborative. As many of us, either social scientists that are beginning to look at biological variables, or in the other direction, biological scientists who are beginning to look at social and behavioral variables in their research, it turns out that the existing methods for being able to integrate variables from those two sets of diverse disciplines are inadequate. And the first thing that you realize is as the depth that we go in is we basically add another variable to our regression equation in terms of the level of sophistication that we use when we try to integrate a variable from one of these other disciplines. And so the Biosocial Methods Collaborative is trying to go beyond adding a variable to a regression equation. And today we're going to talk about heterogeneity. And this is the problem that effects vary. And if we don't acknowledge heterogeneity in our models, we can be led astray in terms of the inferences that we can make and what we learn from our data. So I just want to give some very quick examples of how effects vary. So this is a slide from a grant proposal with some of my colleagues at Wayne State. And this involves imaging of breast cancer. This is a breast tumor. And what we see are scatter plots here that indicate over the course of treatment, over multiple weeks of chemotherapy, a measure of the size and stiffness of the tumor. And what you see, the red curves are best fitting exponential curves. So different participants, different pilot subjects, have different curves. They pretty much follow an exponential, although there's some severe exceptions, such as this one who's not following an exponential, and quite a bit of noise for some participants. But the response to the chemotherapy varies by each individual person. If we also look at behavioral data that's collected during chemotherapy in terms of physical and psychological responses to chemotherapy, nausea, fatigue, emotional reaction during chemo, some participants are pretty stable in terms of reporting sort of high levels of functioning during their chemotherapy. Other individuals, this is on the same scale, other individuals have dramatic responses in terms of their well-being and functioning during the course of chemotherapy. So there's quite a bit of variability both on the biological, the tumor response to chemo, as well as the psychosocial responses to chemo. And we can also look at different medications that are taken for side effects, and we can look at when the patient takes the medicine, how that affects their psychological response to chemo, and we can connect both of those variables to the tumor response. Okay. Let's look at interactions between biological and social variables for heterogeneity. This is a slide from a science article, Caspi and Moffitt and colleagues. And if you look at this, this is demonstrating the interaction between gene and environment. And if you've done social science for a while, you know that social science data don't look this orderly, right? So these are not data, these are simply the point estimates from a regression model. So these are the y-hats, the predicted values. The fact that these curves are not parallel suggests an interaction, suggests that the effect of biology, in this case SNPs, and social science variables, such as stressful life events, has severe impacts on outcomes, such as depression, suicide attempts, and so on. Well, what do actual data look like? Since these are not data, these are point estimates from a regression model. Well, in one project that I've recently become involved in with the Fragile Families, and Coulter Mitchell is a collaborator on this, and many others, we're looking at a particular gene by environment interaction. The environment in this case is a measure of poverty, the percentage of students at the school who participate in the subsidized school lunch program. The phenotype we're looking at, the outcome variable, is the BMI percentile. And we're looking in, today I'll just show you one of the several genes that were examined. But if you do the standard plots, the regression model prediction, we see sort of this very beautiful plot that shows two straight lines that are non-parallel, suggesting an interaction. When we look at the actual data, the data are quite noisy, or there's quite a bit of heterogeneity. The vertical axis is the BMI percentile, and I described it in terms of the full range from 1 to 99. And the horizontal axis is the percentage of students at the school that the subject attends in terms of the percentage of school lunch program participation. And we have two alleles, the risky allele and the non-risky allele. And you see that it's all over the map, right? There's an order to it. If you do a regression of some kind, or you smooth the data, you'll see that there is an order to it, but there's quite a bit of variability. And this is the variability that I think is interesting that we need to understand. We know from behavioral work and decision making that people have different utility functions. People distort probabilities in different ways. So if you're trying to understand patient care, sort of patient-centered care, and trying to bring in medical decision-making with multiple constituents, you need to know the different utility functions and distortions of risk that might be present in the individuals that you're trying to help. With eating, there's quite a bit of heterogeneity in terms of how people respond to food. So I'll spend more time describing this particular display at my talk. For now, what I want to show you is that in this region of one subject's triangle, which is the triangle on the left, you see a lot of yellow. But for a different participant on the right, that same region shows a lot of red. And for our purposes today, what I want to use this to highlight is that the same composition of meal in terms of the percent protein, carbs, and fat, is responded to in very different ways by two different people in the satiety ratings when they consume that meal. So when the meal is made up of about 20% protein, 20% fat, and the rest carbs, one individual has high satiety and a different individual has relatively low satiety. Right? So if we want to develop treatments for obesity, we need to be mindful of this heterogeneity, that people respond differently to compositions of meals. Behaviorally, we know that trajectories differ across individuals. These are 240 trajectories that are classified. I'll go into more detail at my talk for this plot. What I want to show you is the standard spaghetti plot. People in behavioral sciences call the spaghetti plot because you have curves going all different ways, much like spaghetti boiling in hot water. And these trajectories are the response of an older sib to becoming a sibling. So these are families in which there's an only child, and then mom becomes pregnant with the second child, and the older child is followed during the first year of siblinghood. And the dependent variable is aggression, and we see that there are 18 individuals that after about the first month start to act out, the first month of being a sibling. Other individuals are not affected at all by that siblinghood transition. There are some individuals that, even though they start at the same place, have very different trajectories. So these are the two ovals there depict two points or two classes of trajectories. They have essentially the same prenatal with respect to the second born, level of aggression on the older sib. But if you're a parent of that older sib, you definitely want to be able to know whether you're going to be in the upper left or in the lower right class. Right? So what produces heterogeneity? Well, there are many, many different causes or culprits of heterogeneity. Sometimes the process is inherently stochastic. And a very simple example of this is how we see. So retinal cells are sensitive. There are proteins in retinal cells that are sensitive to photons. And the particular cell will fire if it hits, if the number of photons that hit the cell exceed a threshold. 6 or 7 photons can make some cells fire. And then we see, essentially, right? This, I've oversimplified the process. But because photons are hitting the retina following the stochastic process, it's a Poisson distribution, there's already inherent stochasticity in our vision. And we can model that because we understand it. Other processes are more complex and multi-determined. Other processes we simply don't understand. So we see all this noise, and it looks, unsystematic to us. And it could very well be that we just don't understand the processes yet. And of course, there are many, many other sources of heterogeneity. I noticed a science article that came out last week that makes a claim that's being debated quite loudly in the blogosphere, that there's a systematic pattern between lifetime risk for cancer and the cell divisions that occur in that particular organ. So organs that have cells that divide rapidly, in other words, the potential for mutation is relatively high, as opposed to organs that divide less frequently, so the potential for mutations is less. There's a systematic pattern. On the left, we have relatively few stem cell divisions during the lifetime of the organ, all the way to the right where there are relatively many. The vertical axis in the science article is lifetime risk. And you see that for the 31 different cancers that are displayed here, there's a pattern, a scatter plot relation here. The correlation is 0.8. So 65% of the variance is accounted for. The article goes on to make several mistakes that many of us who teach social and behavioral scientists have to train our freshmen and sophomores not to make. First mistake is confusing causality for correlation, and the second mistake is confusing the levels of analysis. An inter confused with an intra. And so the article interpreted this inter-organ relation with an intra account of cancer. That's 65% of cancer variability is accounted for by cell division. But the point of today's talk is the dramatic heterogeneity that there is in the way the body responds to processes like cell division and relations that might play out on processes such as cancer. Now, different disciplines take different approaches to how they handle heterogeneity. And today we're going to hear one approach, which is the statistical econometric approach to heterogeneity. And I hope that through our discussion, we'll be able to tackle some of the other approaches that are out there in different disciplines. So I'll turn it over right on time to our speaker, Jeff Smith. He's in our economics department, and as with most faculty at Michigan, he has many, many appointments. His Ph.D. is from the University of Chicago, and he's been at Michigan since 2005. So welcome, Jeff.
Thank you. All right, thanks so much for the invitation. I've already learned a lot. I've learned where these news reports about most cancer is random come from, and apparently I should no longer believe those news reports, so that's good to know. This is me. That's my email address if you want to get in touch. When you show up, even when you show up in 2005 and you are a Jeff S. Or a J. Smith, actually more to the point, there are not a lot of options for email addresses, and so I picked something memorable. Who the heck am I? As mentioned, I did my Ph.D. at Chicago. I was supervised by this guy that you might have heard of. It was kind of crazy, but I learned a lot. And my first job was up the road at Western Ontario. Then I went to Maryland for 4 years, and then out of the blue got an email from Gary Solon, actually, saying, do you want to come to Michigan and give a job talk? I said, well, sure, but don't you guys have enough labor economists already? I didn't say that part. Glad to be here. Lots of affiliations. I'm a relatively interdisciplinary guy by the standards of economists. So today's discussion, which a better title for, as Rich hinted in his last slide, might be how economists think about treatment effects heterogeneity. My discussion is to some degree influenced by interactions with Susan Murphy and Ben Hansen and other people in the quantitative methodology program that actually meets in this room now, or this half of this room. But I'm not, although I just got my first co-authored publication in health economics, I am not a health economist, nor a physician or any of those things, but I'm going to do my best to define my terms and to be careful about words that are used in different ways in different fields. I'm happy to be interrupted with clarifying questions. I'm going to try to stop with 15 or 20 minutes at the end for more substantive discussion. But if I start using jargon and it doesn't make any sense, put the hand up. Okay, what do I work on most of the time? So I do a lot of stuff. Some of this is methodological. I have a lot of papers about the methodology of social experiments. I have a lot of papers on non-experimental methods, including matching and regression discontinuity. This is another area where there's different literatures in different fields that don't pay much attention to each other, like the literature on heterogeneous treatment effects. I have a paper that some of you might have seen. I presented it in this building on asking people whether or not programs work and whether that means anything or treatments work. I don't know if people do that in health or not. If people do, I'd love to hear about it. And then substantively, I tend to work on performance management, active labor market programs, and issues related to university quality and their labor market effects. Yep. So my goal today, a brief, accessible introduction to how economists think about the issue of heterogeneous treatment effects. There's a sense in which this is a bit narrower than what was laid out in the introduction. That was sort of all heterogeneity, what I would think of as sort of the variance of the error term, as well as the variance in the treatment effect, perhaps. I'm going to focus today on variance of the treatment effect, thinking about treatment pretty generically. So in my world, and at least in some adjacent worlds, I think in epidemiology they use this framework, and in statistics they do, and in other social sciences they do. Though it goes by different names. I like to somewhat facetiously call this the Frost, Fisher, Neyman, Roy, Quant, Ruben model. Some places would cross all those out and just call it their Ruben model. Other places would just have Naaman and Ruben. Here I have in mind the famous poem, The Road Not Taken, which actually predates all of these people. Whoever invented it, it's very useful. And we want to think about there being some outcome. It can be continuous, it can be discrete, and the outcome has one value in the world where a given unit, think about a person, think about a state, it can be anything like that, I guess, for health-oriented applications or biology-oriented applications, maybe a person or an animal. There's an outcome where they receive in the world where they receive the treatment, and there's an outcome in the world where they don't receive the treatment. And the individual specific treatment effect then is going to be the difference between those two outcomes, so y1 minus y0. The fundamental problem that we have is that at most we observe one of these two things for each unit because you can't be both treated and not treated at the same time. And if we observe them in sequence, the unit goes from being untreated to being treated, we don't know that the outcome in the period when the unit is treated is well proxied. The untreated outcome in that period is well proxied by the untreated outcome in the preceding period. In my world, the world of active labor market programs, that is a very bad idea because usually people are unemployed before they're in the active labor market program. Even if they don't take the program, they probably get employed at some point afterwards, and so the pre-program Y0 is not a good proxy for the post-program Y0. That's going to vary by context. I want D to be an indicator for wanting to participate in the treatment, wanting to be treated, trying to be treated, and in general being treated unless we are running an experiment, in which case we are going to randomly assign some units that wanted to be treated to experience by force the untreated state. So R is going to be an indicator for randomization into a treatment group equal to 1 or a control group equal to 0 among people who attempted to be treated. So I have voluntary treatments in mind here. We can think also about mandatory treatments, but maybe we should have in our heads a running example. I'm going to try to use a sort of voluntary smoking cessation program as my example. So that has a health flavor, but it still sounds social sciencey enough to make me comfortable. Talking about drug treatments and all that kind of stuff, I feel like I'm out of my depth. In economics land, we usually focus on one of two parameters. The first parameter is so-called effective treatment on the treated. Some people call that the TOTE. Some people call that for treatment on the treated, the average treatment effect on the treated, or just the ATT, or just the TT. So many acronyms, so little time. The substance is that it's the expected value of the difference between the treated and the untreated outcome for the people who wanted to be treated. That's the on the treated part. So it's people who showed up to the smoking cessation program, and for them, the difference between the world in which they actually get the program and the world in which they do not get the program. We can rewrite that as the expected outcome with the program for those folks and the expected outcome without the program or treatment for those folks. This part's easy, right? This is just the mean outcome of the treated units. We observe that. This is the tricky part, the so-called counterfactual, the unobserved counterfactual. What would have happened in terms of smoking-related outcomes to the people who took the smoking cessation program had they not taken the program? And of course, the whole game is trying to get this. In an experiment, we get this by taking d equals 1 people and forcibly excluding them from the program and measuring their outcomes. In the world of observational or non-experimental analyses, we do econometrics, typically on untreated units that did not try to participate in the program. We beat on them with our econometrics or our statistics and try to get a compelling estimate of that. Today, I'm kind of going to assume all the way through that we have done random assignment, just to sort of separate out the selection issue from the heterogeneity issue. All the things I'm going to talk about port over to the non-experimental world with the addition of the fact that you have to somehow deal with the problem of non-random selection at a treatment. We might also be interested in, actually, this is all average effective treatment on the treated. And this is just how we estimated in the experiment by comparing the treatment group to the control group. Now, why would you think? I mean, Rich tried to motivate this, but let me motivate it a little bit differently here. Why would we think that there might be heterogeneous effects of treatment? Why not just say the effect? If you read newspaper articles, if you read most journal articles, at least in my world, people will talk about the effect of a policy or program or treatment as if it were the same for every unit. Why isn't it? Why wouldn't it be the same for every unit? One reason it might not be the same for every unit is that in fact, in many cases, when we code up a 1, a d equals 1, a treated thing, that actually we're covering up a whole bunch of heterogeneity in the nature of the treatment. So think about a home visiting program for the parents of at-risk newborns, right? So some sort of nurse or something goes out to the house of the at-risk newborn and gives instruction to the parent on health-related issues and parenting-related issues. We say the people who received the home visit, they have a 1, the people who didn't have a 0. But in fact, if the program is of any size, we're going to have several different nurses going out to visit parents to provide this information and assistance. Some of those nurses are going to be very good at doing it. Some of those nurses are not going to be good. Even if they're equally good, some of the nurses are going to click with some types of parents and some of the nurses are going to click with other types of parents. And so even though we're coding anyone who receives this nurse home visit as a 1, that in fact they are receiving a heterogeneous treatment because some of them are getting different nurses than others are getting. And so one reason why you might expect heterogeneous treatment effects is that in many contexts, not all, right? If we're handing out a pill that's chemically homogeneous, everybody's getting the same treatment. If we are raising the cigarette tax by 10 cents a pack, everybody's getting the same treatment. But in many contexts, our indicator for treatment is actually disguising a lot of treatment heterogeneity. And so we get heterogeneous treatment effects because we have heterogeneous treatments. Other times, we might expect heterogeneous responses even to the same treatment. If we raise the cigarette tax by 20 cents a pack, some people will change their consumption behavior, some people won't. That's going to depend on a whole bunch of different characteristics of the person, how much they really love the cigarettes, what their income is, all kinds of different things. That's a case where an identical treatment yields a heterogeneous treatment effect. So it varies case by case, but I think usually if you sit down and think about it, and I will say nothing about strictly biological context, but in any case where there's a sort of social aspect to this thing, I feel confident in saying it's likely that you can come up with a story as to why there would be some heterogeneity in the treatment effects. And so we need to pay attention to them in our empirical analyses, and maybe at least, as I'm going to advocate as I go forward, at least try to investigate in given contexts whether there is evidence that there are likely to be heterogeneous treatment effects. All right, so the rest of this talk, I'm going to kind of do 4 things, I guess. One thing I'm going to do is I'm going to talk about this literature that tries to get a handle on other parameters that depend on the joint distribution of the treated and untreated outcomes. And let me talk about that in a second. Then I'm going to talk about quantile treatment effects. Then I'm going to talk about random coefficient models, which are a standard way in a lot of literatures to think about heterogeneity and the effects of a variable. And then I'm going to talk about subgroups defined by observed characteristics of the units or the context and how to think about those. These are all issues that economists have spent some time thinking about. I think they're all issues that we haven't finished thinking about. Some of them are issues that other literatures have also talked about or indeed kind of moved first on, which I think is the case with the random coefficient models. But I think they're all cases too where there's gains from trade, if you will. Cross-disciplinary arbitrage opportunities exist. And I know there are some students in the room, and perhaps I can interest them or inspire them to engage in cross-disciplinary arbitrage that will be interesting to me and useful to them. I've reached that stage of life where I feel very comfortable giving out paper ideas because I have enough that if I did them all, I'd be dead. So there we go. It's a different stage of life. It is. Anyway, okay. If we run an experiment, what do we get? We get 2 marginal distributions. The treatment group gives us the marginal distribution of the treated outcome. So f of y1, remember I'm imagining that we're doing our random assignment conditional on people wanting to be in the program. So d equals 1. They want to come and be in the smoking cessation program. And then I randomize some of those people, and that should be a 0. Sorry about that. I randomize some of those people to be over here. They realize y1. I randomize some of them to be over here. They realize y0. These are marginal distributions. There's also lurking in the background a joint distribution, and there should actually be no r there. That's very bad. The joint distribution gives me the relationship between the treated outcome and the untreated outcome. Do units that have good treated outcomes also have good untreated outcomes? Right? A natural kind of model that you might think of as a sort of one-dimensional model where there's people who are good at changing their behavior and people who are not, and so they do well in the treated state, they do well in the untreated state. You can think about educational interventions. More able students might do well with the extra bonus course and do well without the extra bonus course, that sort of thing. But it doesn't have to be that way. Now, even if we have experimental data, we don't know much about this. Right? Experimental data are this and this. The marginal distribution of the treated outcome in the treatment group, the marginal distribution of the untreated outcome in the control group. This one strand of literature in economics has said, well, hey, wait a minute. If we could learn about this joint distribution, if we could come up with some plausible assumptions that would link the distributions of y1 and y0, then we could learn about all kinds of really interesting parameters. So, for example, we could learn the fraction of units that have a positive or negative effect of the treatment. Right? You can imagine some treatments that would actually make people worse off. Right? Think about that smoking cessation program. Maybe it stresses some people out. And because they get stressed out by all the pressure to quit smoking, they smoke more. Could happen, right? You can think about active labor market programs, right? You take a guy and you put him in a class for a year and a half. He's not out searching for a job during the class. And if it turns out that the class is teaching some set of skills that are a bad match for the trainee, you may cause not just an impact in the short run, but maybe a negative impact even in the medium or long run. So it's not unheard of that you could have some folks who benefit, some folks who lose from a treatment. We can think about the variance of the impacts. Come back to that in the case of the random coefficient model. That's really interesting to know. How heterogeneous are the effects of a treatment? If they're really heterogeneous, that says, hey, there's a lot of scope to figure out who the big winners are and focus the treatment on them, and also a lot of benefit from figuring out who the big losers are and making sure they don't get the treatment. If the treatment effects are very homogeneous, there is no benefit really from doing that. We either just want to give it to everybody or not. That's important information for treatment design, for sort of treatment institution design. So this paper, this was actually my job market paper back in the day, Heckman, Smith, and Clements, was sort of the first paper in economics literature to bring together some of these results and statistics on bounds. So it turns out there's a couple of old papers, Freshchet and Hoeffding, back from the middle of the last century. And what they do is they show, and I'm going to give an example in a second, they show that the marginals impose some limitations on the joint. Right? So I know the distribution of treated outcomes, I know the distribution of untreated outcomes. They don't pin down exactly what the joint distribution is, but they rule out some possible joint distributions. And as a result, they rule out some possible values of some of these parameters. So that's kind of cool. So this, going too fast. I always think that these things should have like a little mechanism that generates an electric shock. And that if you move both backwards and forwards within like 5 seconds, it should go zzz and punish you for doing that. That may be a bad health intervention though, I don't know. This is another paper that covers some of the same ground. Jabari is a student of mine from when I was at the University of Maryland. This is sort of the paper, this paper, how I would have written it in hindsight. A simple example. Let's think about a binary treatment. I should have, but did not recast this in terms of the smoking cessation treatment. But so let's cross out employment here, and let's think about this as being a heavy smoker is our outcome variable. And so we have a 2x2 table, right? And we have the marginal distributions of outcomes for the control group that doesn't receive the smoking cessation treatment. They can be a heavy smoker or not in the post period. And then we have the marginal distribution of outcomes for the treatment group. They can be a heavy smoker or not, heavy smoker being the analog employment here. So let's think about employed as being the good outcome, I guess, so not being a heavy smoker. So maybe the untreated units, 60% of them are not heavy smokers in the post period, 40% of them are. Among the treated units, we have an effective on average treatment here. It reduces the probability that you are a heavy smoker by 0.2. 0.8 are not heavy smokers, and 0.2 are heavy smokers. What can we learn from these two marginal distributions about the joint distribution of y1 and y0, about smoking status in the treated state, smoking status in the untreated state, and then what can we learn about the distribution of treatment effects? So this is the formula here for the Freshchet-Hoeffding bounds. So this is the CDF of the joint distribution, cap F of y1 and y0. It is bounded from above by the CDF of the marginal, evaluated at the same two values. Right? The joint can't exceed the marginals. The intuition is pretty clear there. Right? So if the joint is 0, 0, then you can't have more than you have zeros in either of the two marginal distributions in the 0, 0 joint cell. That's what this is saying. Over here, we have the sum of the two CDFs minus 1 and 0. We're going to take the max of that. Right? So this thing can't be below 0. It's a CDF. If the sum of the two marginal CDFs is over 1, then we have to do some sharing. Right? So think about, suppose we had 0.6. Well, we do have 0.6 and 0.8 in the good outcome in the control group and the treatment group respectively. We can't put these all in the 0, 1 cell and put all these in the 1, 0 cell because they sum up to more than 1. And the 4 cell probabilities can't in a total sum up to more than 1. That's essentially the information that's being used in this lower bound. So if you plug in these numbers in my little example, so F1 of 0, this is the CDF in the treated state for the bad outcome, it's 0.2. That's just that up here. And the bad outcome in the control state, 0.4. Over here, you get a 0. Not surprisingly, 0.2 plus 0.4 minus 1 is minus 0.06. The max of that in 0 is 0. Over here, the min of 0.2 and 0.4 is 0.2. So the Freshchet-Hoeffding bounds in this example say that the 0, 0 cell has between 0.0 and 0.2 of the probability mass in it. So that's kind of cool, right? That's information. It's not point identification. It's not an exact number because the marginals in general don't provide enough information to give us the exact number. But it is information. It narrows down the set of things that can be true. In the case of a continuous outcome, you can think about these joint distributions as being summarized by the rank correlation between y0 and y1. So in this vector here, now let's think about the continuous outcome. Let's say number of cigarettes smoked in a month, right? And so we have, this is the control group. We arrange them in order from the most cigarettes smoked in the month to the least. This is the treatment group, most cigarettes smoked in the month to the least. If they are the same size, we can treat these as estimates of the corresponding quantiles. If not, we can collapse them to percentiles or something. And then we can think about these arrows as summarizing the joint distribution. Which treated outcome goes with which untreated outcome? One simple case that I mentioned before is the case of rank preservation. That's the case where the counterfactual for each rank in the treated outcome distribution is the corresponding rank in the untreated outcome distribution. That's a strong assumption, but a not unreasonable one in some contexts. You would want to make a case for it. It turns out that you can show formally that rank preservation minimizes the variance of the impacts of the treatment. If the highest number of cigarettes in the treated state goes with the highest number of cigarettes in the untreated state, that difference probably ain't going to be that big, even if the treatment is effective. Boom, boom, boom. If we had inverse ranking, then we're going to have the highest with the lowest and the lowest with the highest. That's going to give us really big impacts. Also implicit in this is a test of whether or not the variance of the impacts is greater than 0. So if you take the rank preserved set of impacts, right? So if you take the treated units in order, the untreated units in order, difference across, that gives you a distribution, a set of impacts. You can essentially test whether those impacts are all the same. If those impacts are statistically all the same, then you don't reject the null of a common treatment effect, of homogeneous treatment effects. If those impacts under rank preservation, because rank preservation minimizes the impact variance. So we can look there and do our test of the null that the variance of impacts is 0. If we fail to reject the null, we might say, hey, heterogeneous treatment effect's not so important here. That test is not that hard to do. You have to be a little careful because you're at the boundary of the parameter space, and being at boundaries of parameter spaces always cause trouble, right? The variance of the impacts can't be negative. It can't be lower than 0 because variances have to be positive. That's what it means to say we're at the boundary of the parameter space. So statistical tests are always a little bit more challenging when you're at the boundary of the parameter space, but it's not that challenging to do. And yet, it's not routinely done. This puzzles me. It seems like whenever people run experiments, they ought to look right away and say, okay, let's test the null. Let's test the null of homogeneous treatment effects. Every time I've seen somebody do it, they reject the null. Then that says, hey, there's some heterogeneity here I should go out and look for. I should go out and try to capture it with my observed characteristics. And that's what we're going to talk about in a few minutes when we get to subgroups. So this is cool. There's a test. You can test the null of impact homogeneity pretty simply. It's discussed in here. It's discussed in Jabari and Smith. I don't understand why we don't routinely do that. It seems very informative. In addition to testing it, you can also get a lower bound. So for many parameters, it turns out that the rank preservation value of the parameter, like the impact variance, is the one that provides an upper or lower bound. In the case of the impact variance, it's a lower bound. That's really interesting to have a lower bound on the impact variance. If that lower bound is really big, that says treatment effect heterogeneity is really important. That's information right there, easy to get, and we don't usually go get it. And I don't quite understand why, but there you go. That's topic number one. Topic number two, which is somewhat related, is quantile treatment effects. And this is something that has come into economics in the last 20 years or so, although you can go back and find precursors inside and outside of economics before that. And the idea is just to do this thing that I described before, is to line up, say, percentiles of the treated outcome distribution, percentiles of the untreated distribution, take differences across. Those are the quantile treatment effects. You can interpret the quantile treatment effects in two ways. One way is to assume rank preservation. If you assume rank preservation, then a given quantile in the treated outcome distribution is the counterfactual for the same quantile in the control outcome distribution. But you don't have to assume that. Maybe you don't like rank preservation. Maybe you have followed Bittler, Gelbach, and Hoynes. They have a test of rank preservation. I'll tell you about it in a second. Maybe you have done their test and you have concluded that rank preservation does not hold in your context. It is nonetheless true that in many contexts the quantile differences are still interesting. Right? So suppose that we thought about let's take our continuous outcome with the smoking cessation treatment again. Right? So we can take number of cigarettes smoked in the month, number of cigarettes smoked in the month in the post period, take differences across. It might be the case when we do that the graph looked like this. So this is actually a graph of quantile differences from a job training program. This is from the Heckman, Smith, and Clements paper. This is the Job Training Partnership Act. These are earnings in the 18 months after random assignment. These are quantiles of the distribution of earnings in the 18 months after random assignment. And what you see here is that for the first 22 percentiles, the difference between the earnings quantile in the control distribution and the earnings quantile in the treatment distribution is 0. Why is that? That's because, in fact, earnings in both cases are themselves 0, and 0 minus 0 is 0. So there's no, under rank, if we interpret that as rank preservation, there's no effect in that zone. From about the 25th percentile to about the 95th, the difference is about $800 over 18 months. That's remarkably constant, actually. We were surprised. It's not this constant for other demographic groups besides adult females. And then there's a blip up here. This graph, I would argue, is interesting whether or not you believe rank preservation is true. If you believe that rank preservation is true, it tells you that lots of units have impacts of about $800, except for these folks who are not employed in either state. If rank preservation is false, it still tells you that, well, here's what happens to the distribution of outcomes. There's a bunch of people at the bottom, right? Well, it doesn't have to be the same people, but there's a blob at 0 in both cases, and then the middle part of the distribution kind of shifts over by a constant amount, and then the tail shifts by a little more. Even if you don't believe rank preservation, so you don't want to say that this is the impact on the person at this percentile, that's still interesting to know what happens to the distribution. And you could, for example, calculate measures of inequality here in the treatment group and the control group, and that would be interesting to do. So quantile differences are interesting. Moreover, it turns out that the quantile treatment effects correspond to the impacts under rank preservation. So the quantile treatment effects are the treatment effects at that bounding distribution that minimizes the variance of the impacts. And so that test I was talking about is really just a test of whether all these quantile treatment effects are equal. And this is just a bunch of quantile regressions, essentially run for every 5th percentile here. You could run it for every individual percentile. And then in Stata, one easy command in Stata, you could test the null of homogeneous treatment effects, and yet we never do, or almost never do. What is the test? This is really cool. This is one of those papers where you read it and you say, I could have written that paper, darn it, right? Where it's obvious after you read the paper, and you realize that you could have had the idea, and you could have written the cool paper, and you didn't do it, they did it first. It's very frustrating, but it's a very cool idea. So their idea is that if rank preservation is true, then if I look at the people in the treatment group at the median and the control group at the median, they should have the same observed characteristics, where these characteristics are characteristics that are not affected by treatment. And they propose a formal test of that implication of rank preservation. It's a very clever idea. And oddly, the journal editor made them take the test out when they went from the working paper version to the published version, because the paper was not mainly about the test, it was mainly a substantive application. And I don't know who that editor was, but they were very silly, because to me the test is the really interesting part of the paper. All right, here we go. So that's what I want to say about quantile treatment effects. They're related to this issue of bounding the joint distribution and rank preservation. Let me now switch gears a little bit and talk about random, question, sorry, thank you.
When people publish papers like this, do they start out by showing the CDFs out of which data like you had in the last graph are obtained?
We provide descriptive statistics.
There are CDFs for
Yeah.
each of the groups.
Yes, there are.
Give you that, right?
Yes.
Do those get shown at the beginning before all of these other derivative analyses are performed?
We present descriptive statistics on selected percentiles of the two CDFs. We don't literally graph the CDFs.
Is there a reason for that?
Graphs take a lot of space relative to tables, I think is probably the reason.
Would you have more intuitions about what's really going on if you were able to see the individual CDFs for each of the groups?
Yeah, perhaps. I mean, if you were really clever, you could put them all in the same graph, I suppose.
I'm just curious why one doesn't get down and dirty to begin with before going into all these summary analyses.
Yeah, that's a good point. I'm with you on that. I think in general, the margin at which a lot of economics papers are operating, unfortunately, is there even a table of descriptive statistics before we get to the multivariate analysis? I agree. A picture of the CDF, especially for things like this, even better. Let me say a bit about random coefficient models now. And random coefficient models are very popular in some parts of the world. So in the education world, our unfortunately former colleague Steve Raudenbush, now at Chicago, was like Mr. HLM, Mr. Hierarchical Linear Model. And hierarchical linear models are in some sense all about random coefficients. And when I think about random coefficients, what do I mean? I mean heterogeneous treatment effects, so heterogeneous coefficients on the treatment indicator that are not correlated with anything else, hence the name random. You have to be very careful here because the HLM world, for example, uses the terms fixed coefficient and random coefficient to mean different things than economists do. So I want to be very careful about that. But what I mean when I say random coefficient models is models where I assume that there are heterogeneous treatment effects. So there's a random coefficient on my treatment indicator, but the heterogeneous treatment effects are unrelated to everything else. So in particular, they're independent of Y0 and they're independent of D. Right? So they're independent of whether you want it to be in the treatment or not, and they're independent of the untreated outcome. Those are both really strong assumptions, at least the way I think about it. So if you write down a standard economic model of participation in treatments, and you assume that the agent who is deciding, maybe it's the person who's going to be treated, maybe it's their position or something, that the agent who is deciding about whether or not the unit gets treated knows something about the treatment effect, that ought to influence whether or not they get treated. Right? Well, if the treatment effect or some fuzzy estimate of it that has some information in it affects whether or not you get treated, then the treatment effect is correlated with D, which violates the random coefficient assumption. Whether or not the treatment effect is correlated with the untreated outcome, that's sort of more a technological concern, right? We could think about contexts where that might be true. We can think about contexts where that might be false. But I worry that it's hard to write down a model of voluntary treatment choice in which agents have any information about the treatment effect in which the treatment effect is not correlated with the treatment. And if the treatment effect is not correlated with the treatment, then the random coefficient model and the assumptions that it embodies are incorrect and give us bias estimates. That's my economist rant about why I don't like random coefficient models. I do like random coefficient models in the following sense. They're better than common coefficient models because they're paying attention to the fact that treatments probably have heterogeneous effects. I don't dislike HLM and MLM because I think they're often very valuable tools in sort of framing the underlying causal processes. They're sort of valuable in a pedagogical sense almost. Anyway, let's suppose for the moment that we believe that the random effects assumptions are true. Then the variance of y1, the treated outcome, is equal to the variance of y0 plus the treatment effect. And because I've assumed that the treatment effect is independent of y0, the variance of the sum is the sum of the variances. There's no covariance term to worry about. Thus, I can recover the variance of the treatment effect as just the difference in the variances between the treated units and the untreated units. And that gives me another test, right? If I calculate this, an estimate of this and an estimate of this, subtract one from the other, and get a negative number, I have rejected the random coefficient model because the variances can't be negative. And indeed, there was one of the 4 demographic groups in this job training experiment that I mentioned before where we could indeed do just that, where the variance of the outcome in the control group was higher than the variance of the outcome in the treatment group. So the random coefficient model had to be wrong. I don't see people do that test either. The economics or econometrics literature has gone down some roads here, being more flexible than just assuming a normal distribution for the random effects. You can even follow the electrical engineers, as we did in Heckman, Smith, and Clements, and non-parametrically deconvolve the treated and control outcome distributions to get a non-parametric estimate of the treatment effect distribution. Maybe. All right, subgroup effects. Topic number 3. What works for whom? So in this paper with my student, Habiba Jabari, we make a distinction between what we call systematic variation in the treatment effect and idiosyncratic variation in the treatment effect. And what we have in mind is that systematic variation in the treatment effect is the variation that you can capture with observed covariates. Those covariates may describe the units, or they may describe the context. So in the smoking cessation example, right, a unit characteristic might be age. Maybe younger people are more responsive to smoking cessation treatments as they have a longer life period over which to realize the benefits of the treatment. Context effect might be how many other people in the family smoke or in the household smoke, right? And that may affect the treatment effect. If we estimate, going back to what we talked about before, right? In my ideal study, you sort of come in and you estimate the lower bound on the treatment effect variance. That's some number. And then you go looking for systematic variance, or what I'm going to call subgroup effects here. And maybe you find that the subgroup effects that you can identify in the data account for a lot of the total variance, or maybe they account for only a little of the total variance. That to me then means that there's a further research program that says, well, suppose I find that there's a very high lower bound on the variance of the treatment effects, but that the subgroup effects that I can estimate using my existing covariates capture very little of that variation of the treatment effect. Then I need to sit down and think about, okay, what is my theory, whatever my substantive theory is in my area of interest, what does my theory suggest are the variables that should capture heterogeneity in the treatment effect? And then I should try to measure those the next time I go out and collect data and see if I'm right. Because systematic variation in treatment effects is much more useful than idiosyncratic variation in treatment effects. Systematic variation in treatment effects can be used for statistical treatment rules or targeting. So some examples of statistical treatment rules, the one that you'll probably be familiar with is SMART. This is Susan Murphy's clever acronym, right, for sequential multiple assignment randomized trial. Susan Murphy's work, much of it is about statistical treatment rules in the context of mental health and other health domains. Now she's working on addiction, sequences of addiction treatments. In my world, there is something called the Worker Profiling and Reemployment Services System. that tries to assign reemployment services to the people who benefit from them the most. In the education world, there is a whole genre of treatments called RTI, which is not Research Triangle Institute. It is response to intervention. And the idea there, again, is to use characteristics of learners to assign them to particular treatments so as to maximize the total amount of learning, right? To systematically exploit systematic variation in the treatment effect by assigning the treatment or assigning specific treatments from a set of treatments to those who are estimated based on subgroup effects to benefit from them the most. That's a noble technocratic goal, right? If we were really good at this, we could realize a lot of gains relative to the current world. If we could assign people to the right college major, if we could assign them to the right medicine, where there's, in cases where there's multiple treatments and some people respond more to one and some people respond more to the other, there's lots of potential gains to be realized in many substantive domains from uncovering systematic variation in treatment effects. And this is something economists have thought a bit about. In particular, Charles Mansky, another Wisconsin connection, we were talking about Wisconsin before, now at Northwestern, has thought a lot about these things. Let me now discuss some issues having to do with subgroup effects. And these are issues that I know have also been discussed in other areas. So this is a point that isn't discussed very much in the economics literature that I think is important. It involves another word that is used completely differently in different fields. So let me be very careful. And that word is structural. So are subgroup effects structural in the economic sense? And here the economic sense means sort of policy invariant. If you read the papers by Mansky and other people on statistical treatment rules, they act as if, you sort of estimate heterogeneous effects and you say, oh, this treatment is better for men than women, this treatment is better for old people than young people, whatever, this treatment is better for high education people, low education people. They act like those are sort of fixed facts that are independent of however you selected people from those populations into your study. So that then you can take those facts and you can say, well, let's serve this group less because their impact is small and this group more because their impact is big. So I have a little example here in which that is not true. So in my example in which that is not true, suppose we have some treatment. It can be our smoking cessation treatment. This could be number of cigarettes per month. And let's suppose that half of men have an impact of 10, half have an impact of 4, half of women have an impact of 12, and half have an impact of 1. So there's heterogeneous treatment effects within subgroups. And then further, let's suppose that the cost of participating is 5 and that people know their impacts. So who shows up with d is equal to 1 in my notation? The people who show up with d is equal to 1 in my notation are the people whose impacts are better than 5. So it's the men with impacts of 10 and the women with impacts of 12. So they all show up, they have d equals 1. I randomly assign them to the treatment or not. I run my impact regression and I interact the treatment indicator with an indicator for being male or female. And I find, lo and behold, that women have a larger impact of treatment in my study by 2. And I say, hey, that's great. We need to subsidize more women to take this program. But of course, in my contrived example that's designed to make this point, the marginal untreated woman has a smaller impact of 1 than the marginal untreated man. Now, you can, of course, imagine less contrived versions of this that still embody the same general point, that the average impact among the people of different subgroups who showed up into your study may not be informative about differences in impacts across subgroups at the margin of the treatment choice. And if the policy that you're considering is moving that margin for the different subgroups, what you really care about is the marginal impact, right? The next person that you serve, the next person that you subsidize to serve, or you somehow cajole into the program, you'd like to be the 4 and not the 1, even if on average these guys are 12 and these guys are 10. This is a point that has not been, this is something I tend to write a paper about, but I haven't gotten around to it yet. But I've been intending to write a paper about it for like a decade. Nobody else has written the paper yet, so all right, I sort of said that. It's nice to have models. Economists like models, you all know that. This is a part of economics that tends to be relatively model-free. And my sense is a part of other disciplines that often tends to be model-free as well. You'll see a paper and it says, oh, well, we're going to go look for heterogeneous treatment effects and we're going to do them by, age, race, sex, and schooling. And there's no paragraph that says, here's why we're doing the heterogeneous treatment effects by age, race, and schooling, and not these other 100 variables that are in our data set. And there are a few, so I've highlighted a few examples here of papers that are not like that actually have models that say, here's why you should expect this subgroup to have a bigger treatment effect than this group. That's this development economics paper by Pitt, Rosenzweig, and Hassan. There's this really nice, this is a different Bittler, Gelbach, and Hoynes paper, where they look at a budget set treatment that's changing sort of the costs and benefits of different activities for welfare recipients in Connecticut. And they show their model, the standard model of the labor leisure choice with transfer programs, actually predicts particular patterns of quantile treatment effects. They go looking for those patterns and they find them. That's really nice, but it's really rare. And then this is another paper. I don't know what the situation is in other disciplines. My sense is in education, again, there's very little theory about why treatment should work better for high income or low income or free and reduced price lunch or not, or men and women. This is a real good road to go. You get more out of the data, you avoid issues of multiple comparisons that I'm about to talk about, and it helps guide future data collection, because theorizing about where the heterogeneous subgroup effects might come from may help guide you in deciding what subgroup information to collect in the data. Okay, I do want to allow some time for discussion. So let me talk a little bit about fishing, probably something you all know about, and then a little bit about external validity, and then I will try to stop at like 13 till and allow time for discussion. Okay. So this is a problem that many disciplines are familiar with, and indeed I think many disciplines spend more time worrying about this than economics does. I know that education spends more time worrying about this than economics does. If I estimate heterogeneous treatment effects for subgroups defined by 100 different variables and use alpha equals 0.05 of my criterion for statistical significance, then on average I'm going to find that there's 5 of those subgroup variables that indeed show heterogeneous treatment effects, even if in fact the treatment effect is common across all the subgroups. And so this is the standard multiple comparisons problem. It often rears its ugly head in subgroups, partly because what happens is, you're at Mathematica and you've been hired to evaluate some program that has lots of positive mojo and that the Department of Education or Health and Human Services really likes, and you do your randomized experiment and you look at the overall treatment effect and it's 0. And you're sad, or it's some smallish number and not statistically different from 0. And so you're hoping to save the thing in the eyes of the client by finding some subgroup, some hook, some hope that can go in the New York Times and say, well, gosh, the Job Corps doesn't pass a cost-benefit test for most of the people it serves, but for people who are 24 and Hispanic, it's a killer. So we need to go down that road. People understand this natural response to disappointing results. And of course, in the education world, there's this thing called the What Works Clearinghouse, which is colloquially known as the Nothing Works Clearinghouse. I really like that name. And is known that for a reason, because most educational interventions don't actually work. And so if you're in that kind of world where zeros are coming up all the time, you go fishing. What has been the response in economics? Well, I think one response, maybe it should be 0 here, is to motivate your subgroup analyses by a well-defined model, right? To have a reason why you're doing each subgroup analysis. Absent a reason, you can pre-commit. This is very popular in development economics and in economics and now in the education world, is that you say in advance, before you look at the data, these are my confirmatory outcomes and these are my exploratory outcomes. In the world of the Department of Education, you have to do statistical adjustments like Bonferroni or Benjamini and Hochberg for the confirmatory outcomes, but not for the exploratory outcomes. But it's understood that the exploratory outcomes are just designed to motivate choices in the next evaluation down the line, and they're not supposed to show up in the New York Times. You can just do these multiple comparisons adjustments for all of your outcomes. And another thing that's been done in economics is this dimension reduction, right? So if you have 8 different outcomes that are all supposed to be capturing kind of how well you do in school, then you collapse them into some sort of index. So economists in recent years have become great amateur factor analyzers, even though we don't ever teach factor analysis and none of us really knows anything much about it. We now dimension reduce things using principal components and then treat the dimension reduced object as the outcome. Thus we have, instead of 8 outcomes, we have 1. and our problem of multiple comparisons is reduced, of course, our problem of interpreting the result is increased. All right. All this relates to external validity. I'm going to not talk too much of that. External validity, as economists usually do it, just involves estimating subgroup effects as a function of x's and then reweighting them to take account of the distribution of the x's in the target population to which you want to generalize the results from the source population, worrying, of course, along the way about the fact that there may be differences in the support of the x in the source and in the target. I'll leave the rest of that to you to read. And by the way, I have included a reading list here. So if people want, if Rich wants to circulate the slides, you can know where all the papers are that I cited. So summary and conclusions. There's a lot of parameters, right? Once you get into heterogeneous treatment effects land and you get away from the effect, there's actually a whole bunch of interesting treatment effect parameters that are various functions of these underlying individual unit treatment effects that you might be interested in and that address different substantive questions of interest. There's been some work on how to bound or even estimate those parameters under different assumptions. There's a lot to be done here. Most of this work, I think, has happened in economics. Subgroup effects, side effects, context effects, whatever you want to call them, treatment effects that vary with observed variables are really useful and very practical, right? We'd like to be doing statistical treatment rules for all the treatments that we do. That's what personalized medicine is all about, for example. That's my impression. Not as trivial as they might seem for many reasons. I will stop there. Questions?
Take some questions.
Uh-oh.
I have one. So all your examples are univariate. I'm sure that's to keep things simple.
Yes.
For people that are integrating biological and behavioral variables, there's usually a multivariate case. Say if you're doing even with random assignment and experiment, you might be collecting biological data, hormones, bulb response in an imaging study, as well as behavioral data.
Mm-hmm.
You're trying to understand the relation between behavior and biology of some kind.
Mm-hmm.
In some cases, there isn't random assignment. You're collecting data such as genetic data correlated with stressful life events and looking at other outcomes. So how does this attention to detail with respect to heterogeneous outcomes play out in a multivariate case?
So let me clarify your question. So at first I thought you were asking about non-binary treatments, but I don't think that's what you're asking about. I mean, all this can be generalized to continuous treatments. It just gets harder. So you're asking, and is it just that you're asking about multiple outcomes, or you're asking about what about other conditioning variables that I want to stick in there? Multiple outcomes.
You put people in an experiment, put them under different conditions, and you're measuring their cortisol levels, you're measuring the bulb response, you're measuring accuracy rates on a task.
Yeah.
Measured and so on. And each of those individual variables have heterogeneity with respect to the treatment that they were assigned to, right? And you're trying to understand the covariance across those variables. That's sort of a fundamental problem that we have when we try to integrate biological and social science variables.
So let me. I think the answer here is that economists don't do that. But let me offer two other answers. So one, oftentimes there's a lot of outcomes, and you get into the same fishing problem with the outcomes that you had with the interaction, the subgroups.
In advance,
Okay, no, that's great. That's great. But so Perry is the poster child, right? Perry Preschool is the poster child for 15 times as many outcomes as there are observations in the data. And then there's a little literature. There's an Anderson paper that I cited in here that and there's also a competing Heckman paper that tried to deal with that issue. But that's not what you had in mind, because those are all they're all just treated as separate things. We have our 100 outcomes, we run our 100 regressions, we put them in the table, and we sort of count them. The other thing that people worry about in economics a lot is mechanisms / colliders, what the Pearl directed acyclic graph literature would call colliders. And what economists, I'm probably one of 5 economists who know what a collider is, so I'm not even completely sure. But I like the DAG stuff. I wish I knew it as well as some people do. And so if you think about like a training program, you look at the effect on earnings, but you also look at the effect on hours of work and wages of those who work. And you think about those as kind of ways of decomposing the overall effect on the thing you care about the most, which is earnings. How much of it is that some more people could become employed? How much is it that some people who are already employed work more? And how much is it that some of the people who are employed and working a given amount of hours get a higher wage? And you'd like to kind of decompose that way. That's another thing that economists think about. But that's a bit different than what you were describing, which was kind of interrelationships between final outcomes in some sense, not intermediate outcomes. That's not really something economists do. I'd like to have a reference on that.
They are though in terms of, for example, policy changes have an impact on somebody's income or their wealth and their well-being, their quality of life. So there are several economists currently, like Kahneman, Kruger, et al., who are now trying to worry about those things.
Mm-hmm.
So,
But what I hear Rich saying is that they're worried not just about, I'm going to have a table and it's going to have 2 lines in it, and one of them is the effect on the income and the other is the effect on the subjective well-being, is that you want to tie those two together, right? So that there's kind of outcome pairs of income, subjective well-being, and I want to see how the treatment moves people around between those pairs. That's not something I see a lot of. I'm glad to know that Alan, I assume that Alan is the Kruger that you were talking about, is doing that.
yeah.
Question?
Rumor has it that a meeting on the West Coast over the past weekend about these matters was attended by a certain very well-known economist who asserted that economists understand exactly how to deal with these specific matters, whereas psychologists and sociologists are totally confused about them. And I'm wondering whether or not this rumor is in fact true.
I don't know. Who did you have in mind?
This is all anonymous through the rumor mill, but it has been specifically asserted.
It wasn't me.
That's not the question.
I wouldn't have said that.
No, I didn't assume you would have.
Yeah.
I'm just wondering whether the rumor is nevertheless true.
I think it may have been said by a different person in jest.
So your interpretation is that it was totally jestful,
Yeah.
as opposed
Yeah.
to having a serious underlying belief that motivated it to get said.
Yeah, that would be my interpretation,
Thank you.
based on what I know of the person I think involved, and the laughter that occasioned the statement, or that followed the statement. Yes, that was very inside baseball. Sorry.
In medicine, one of the more appealing ways to look at this is with an interaction effect with essentially a reduced, eventually reduced form, predicting the outcome in the control group. In other words, the risk of whatever outcome.
Would you use the term prognostic score?
Yeah.
Okay. Okay.
A risk prognostic score that's existing, that existed independently of the study you're doing. And then it seems like the most natural way to look for these things is through some sort of interaction of the treatment with this risk form, with this risk score, and then a random coefficient based on that. So what would your thoughts? Because it also gives you natural ways to interpret, and actually pretty, in our field, pretty compelling ways to interpret the whatever heterogeneity you see there. But given your lack of interest in random effects models, what would be your way? Would you have a better way of dealing with that?
Well, you made a jump from a subgroup based on a prognostic score to a random effect model, and I wouldn't have made that jump.
No, you could make, essentially then you can look at the random coefficient model in the when you have those interaction terms. But so it's the question is that would that be a way you go back? Those aren't subgroups. They're basically, in fact, you're getting away from subgroups by using this sort of unitary prognostic score.
So you want, let me understand some more. So the prognostic score is continuous, whereas the subgroups are probably binary. And we're going to take the prognostic score and interact it with the treatment indicator.
Right.
And where are the random effects coming in?
Well, okay, so you could.
I mean, maybe these random effects and fixed effects again are one of these pair of terms that people use very differently.
So the interaction of the
prognostic score and the treatment indicator. Does the coefficient on that thing have an I subscript?
right. Initially, it would not.
It would not. Okay, then okay, that's fine. I guess it seems my concern about that, I think that's nice, especially if there's a whole lot of variables and if there's a good theoretical reason to think that the heterogeneity and the treatment effects is working through this index, right, that is the probability of a good or bad outcome in the untreated state. But that is imposing some structure on the process, right? When you go from interacting the treatment indicator with each of the individual covariates that makes up the prognostic score to just interacting the treatment indicator with the prognostic score, you're sort of assuming that all of the covariates work through this index, and that doesn't have to be true, right? There is substantive content to that dimension reduction procedure.
Interacting with all the
Yes.
But remember, of course, at least in our clinical trials, we're already underpowered for detecting the main effects, much less when we start.
That's true of every experiment I have dealt with in social science as well. So,
So in some sense, from a practical standpoint, it's one of the only ways, the subgroup analyses are often horrendously underpowered in most.
yes,
So one of the ways you can try to salvage something.
that makes the whole fishing thing worse, right? It's yeah, no, but that I agree with your practical point that if you're underpowered, that it's good to try to dimension reduce, if only as a response to the fishing issue. But that's a bit different motivation than really believing that that all these things work through this index in a substantive sense. Doesn't mean it's not worth doing in a practical sense.
The random effect part is that basically one of the ways you can think about a random coefficient model as a way to test whether there are likely to be any interaction.
Mm-hmm.
And that's sort of how it's.
But I would want you, instead of doing it through the random coefficient framework, where you're imposing this assumption that the heterogeneous treatment effects are independent of everything, I would have you do it through this bounding exercise that I described, where you don't have to impose that assumption. That I would have you calculate the Freshchet bound on the variance of the treatment effects. That doesn't require imposing the random as a first step. And if you bound it substantially away from zero, then I say, okay, I got to go looking for subgroup effects because there's some heterogeneity here.
And the reason there is because of there are fewer assumptions.
Yes.
Specifically the two you mentioned.
Yes, exactly. We labor economics, which is sort of my nominal home, I guess, went through this phase, right? There was the Heckman selection model, which was very famous and all that stuff. And it relied on making these heroic bivariate normality assumptions to solve the problem of non-random selection to treatment. And there was a period before I got to graduate school when everybody was very excited about that, and it seemed like magic. And it was magic. And then there was this sort of reaction against that in economics, where we went kind of all the other way off to sort of non-parametric identification land, and we didn't want to make any assumptions ever. And I think to some extent where we sort of come back a little bit to maybe a good middle place, where we wanted to make some assumptions that they're well justified. We're not completely terrified of them, but we're not the naive researchers of the 70s. Uh-oh, this may get out in I may get in trouble for this. The naive researchers of the 70s who, given their state of, given what they knew, they were doing a reasonable thing, which was applying the bivariate normal model with no variable that moved participation around independently of the outcome. So that's part of why I like that. That was by way of motivating why I like to do the bounding exercise rather than the random coefficient exercise as a way to get a handle on how much potential heterogeneity there is in the treatment effect, is that I still have a bit of that rebellion against assumptions in my head.
Well, we're out of time. Thank you very much.